Have you ever done a math problem and then you get infinity as your answer, so you just shrug and pretend it's not there? I don't know about you, but that's par for the course for quantum physicists. And it's fine. Somehow quantum field theory is the most accurate scientific model humans have ever produced, and it's not even close. So let me explain why it's not as bad as it sounds. So first things first, infinities show up when computing probabilities in quantum field theory. This is pretty much true for every type of quantum field theory, save a few, so it's not that out of the ordinary. But the reason this happens is that calculating probabilities amounts to adding up the contributions of all possible quantum configurations that can lead to the outcome of interest, and there's an infinite number of them. Now, it turns out that the infinities that appear in the theory can be linked with certain parameters describing the theory. In the quantum theory of electrodynamics, for example, these include the electric charge and the electron mass. If, when doing calculations with a particular theory, we used as inputs the finite measured parameters, then we get infinities. However, if we assume that the input parameters are not the measured parameters, but are instead so-called bare parameters that were infinite, then our calculations would recover the finite values that we measure in the laboratory. Basically, we adjust our description of the mathematics of the theory by adding a term that's infinite. But this infinity will cancel the infinity that would otherwise arise if we used measured parameters. And at first blush, you might say that this is ad hoc and it shouldn't be allowed. But physicists will argue that it's fine, because we shouldn't have assumed that we started with the correct description of the theory to begin with. This idea goes all the way back to Wilson, that all physical theories are effective theories. What this means is that every physical theory should only be expected to make accurate predictions in some range of energy scales or length scales or whatever. If we had an ideal fundamental theory, one might expect to always get finite answers, but we don't have that, so we get something nonsensical. So in order to avoid ending up with useless theories, we instead parameterize our ignorance. The counterterms that we add to remove infinities are viewed as capturing the more fundamental physics that we're missing. And if we're able to do this in a way that is internally consistent, which for many physical theories that we're interested in we can, then that means that the complicated physics that we don't know at very high energies don't play a role at the low energies we really usually work at. At least, it doesn't play a role once we renormalize our theory. The trade-off, of course, is that we lose potential predictive power at those high energies. By packing away all their effects in artificially constructed counterterms, we can't see them anymore. But we gain a theory that is remarkably accurate at low energies, which is pretty handy if you ask me.